of this distinguished lecture series. Bienvenue à tout le monde pour la conférence distinguée. Et nous avons eu Nilima Nigam hier et demain. Et aujourd'hui, c'est Alex Barnett et vendredi aussi. So today is going to be Alex and Friday, and tomorrow one more talk by Nilima. So it's great pleasure to have Alex for this week. We managed to grab him from New York City, which is a beautiful, even more beautiful than weather probably than it is here today. And Alex did, we know each other for a while now, I think, but he did his PhD in Harvard some time ago. And then after his PhD went to actually work in, so was it rheology or something like this in Mass General? And after that stint, I would say a little bit, he went to be an instructor in Courant Institute, where he done a lot of great numerical analysis ever since. After that, Alex moved to Dartmouth, where he was eventually a professor until 2017, 18, something like this. At which time there's a bit of a diffuse boundary going on there. Became the researcher at the Flatiron Institute in New York City, and where he's currently the lead of the numerical analysis group. You call them group.
Yeah.
So Alex has
been,
a little bit. So among the many things that Alex has done, a lot of these recognitions and accolades that he got. One really impresses me. He was first prize of the International Physics Olympiad. So and so you'll see that a lot of his research, while anchored in numerical analysis and mathematics, always has, when you talk about eigenvalues and such, there's always physics lurking around. And so without further ado, let's welcome Alex for a wonderful talk.
Thank you, Jean-Christophe. It's great to be back here. I'm privileged to be part of this nice series, this nice week, and to be speaking alongside Nilima Nigam, who I've also known for a long time, admired her work. So and some of what Nilima talked about will be relevant today. I'm going to talk about fluid flows, Stokes flow in particular. And this is joint work with Anna Broms, who's did a lot of this work as a grad student with Anna Karen Thornburg. Both of them are at KTH. Anna Broms is now a postdoc, and then Daria Malhotra is a local research scientist with us. So we'll see some of his stuff as well. So I just wanted to, okay, something has just appeared. Okay, just wanted to say a little bit about where I work. And so this Flatiron Institute, not to be, here's the Flatiron building, 23rd Street. And then Flatiron Institute is this thing a couple of buildings back behind 21st Street. So just so you know, we're not actually in the building in that one. Anyway, computational math is one of 5 centers. It's sort of filled out to now include biology, which was the first one, and then astrophysics, astronomy, quantum, and neuroscience. And each is about 50 researchers. And CCM has basically 5 groups focused in scientific computing, numerical analysis, biophysics and imaging, computational statistics, and machine learning. So, and what makes us different from academic departments, perhaps the most striking thing is the focus on software development, release, and support. So, okay, I'll tell you a little about my areas. Numerical PDE is maybe the main one, and that includes acoustics and waves and the kind of thing Nilima talked about yesterday. But today I'll talk about viscous fluid flow, which is part of that. But I also spend quite a bit of time on software package for signal processing, something called the non-uniform fast Fourier transform, which is used for a bunch of imaging problems, MRI and such. And then I just end up getting sucked into other computational science areas, like some electronic structure stuff. Oscillatory equations sort of was my early work that came out of the physics work, eigenvalues. But then there's sort of diffusion problems that occur when we talk to the the biologists in the next center. It's a and some statistics. So it's this very collaborative environment where the CCM, we're kind of the people, where people come to when they're stuck on computing problems. So, okay. So today, let me motivate a little bit. One overarching question is, what happens to a fluid, especially what its effect. Remember, the viscosity of a fluid is how much force how much it tries to fight shearing the fluid. So what happens if you throw in a whole bunch of particles that are rigid? How does that shearing, the effective viscosity change? So, and these questions, especially in biology, are down at 0 Reynolds number. So that means no inertial effects. It's just stickiness. And if you stop pushing, everything stops instantaneously. So here's one really beautiful, let me see, that should actually, oh yeah, I've got to come out of these things, sorry. All right, so this is experimental visualization of, this is just plain fluid with a blob of dye in it. And this is the blob of dye with a bunch of spheres dragging that dye around. And it's all at 0 Reynolds number, so there's no turbulence, but you still kind of get turbulent effects and you get mixing. And you can see the fluid is caught next to the spheres and gets dragged along very large distances. So how could you model that? Another sort of motivating now simulation is by some of my colleagues, Wen Yan, well, who's left, unfortunately, but with Mike Shelley's group. This is a bunch of sedimenting spheres. The colors actually show some of the forces when they touch each other, and they're all falling down under gravity in a viscous fluid. And this is just to give you an idea, this takes, on 2,000 compute cores, this takes 2 minutes per time step. So it's running overnight, even on a medium cluster, right? So these are actually difficult calculations to get right. So on the biology side, there's one motivational question is what happens inside cells? You have these structures like long filaments, spherical objects, and then a boundary, and they're all dragging against each other. And then there's active proteins sort of trying to move things around. And there's also sort of other objects like swimmers, which are little particles that have non-zero slip velocity, which means that they're actually, when the fluid's in contact with the particle, it's moving. So the particle then moves through the fluid. So the slip velocity we'll see shortly. These are all motivations for the Stokes problems. So I'll tell you a little bit about incompressible Stokes problems, the math and the challenges. Then I'll talk about the method of fundamental solutions, which is a way to solve like linear constant coefficient PDE, elliptic PDE often. And it's kind of complementary to what Nilima talked about yesterday. So, but it's not often applied in Stokes flow. So that's kind of fun. Then we'll go into detail about what happens when spheres get close to each other. That's where all of that's one source of difficulty. And then finally, I'll overview a little bit about slender bodies, which is thin, skinny objects like filaments being dragged through fluids. And all of the difficulties there, and that will be with boundary integral equations, which is exactly what Nilima talked about. So, okay, but in general, our philosophy, right? Maybe this is sort of obvious to all of you who have already who've fallen in love with numerical analysis. So that you want to design a solver that's convergent. That means you believe the PDE model, and you want to be able to dial in as many digits of accuracy as you want to check that you've actually solved that PDE model. That they're high order accurate, meaning if you want to make, like go from a 3-digit to a 6-digit accurate solution, it doesn't take you that much extra effort. And then finally, if you have 1,000 particles and you want to go to 2,000 particles, it only takes twice the effort, right? So linear scaling in the system size. Okay, so with that said, let's dive into the math. So we have, remember, we're talking about viscous fluids, so basically at 0 Reynolds number. remember that means that if you push the fluid, it moves according to forces, and if you remove those forces, it stops instantaneously. And that's a good model for water or biological fluids down at the cell scale, so micrometer scale. And then also, so you shouldn't go too microscopic in the model, right? There's limits to the model in the other direction, which is if you go down to very small particles, then the atoms and the molecules of the fluid banging against the particles actually causes them all to have Brownian motion, and you end up with a stochastic differential equation, which is a whole nother kettle of fish, as we would say in England. So we're not going to deal with that, although these tools could be like a starting point for solving those. So we're sticking to, well, PDEs and ODEs, but nothing stochastic. Okay, so the boundary value problem is you want to solve for a velocity field U and a pressure P, and in the exterior of all of these objects, right? Each object you can call omega 1 up to omega B. B would be how many objects, like 1,000. You have the Stokes equations. So this locally says, it looks kind of like a Laplace, but it's for a vector quantity, and there's this pressure and velocity. But this just basically says the force is balanced at every point. This says the fluid is incompressible. The next one says that the solution you're looking for dies as you go to infinity. And finally, this says that the objects are going to be moving as rigid bodies. So the boundary conditions you have correspond to velocity plus rotational motion, right? So you've got V's and omegas, like velocities and angular velocities of each body. Okay, so Ladygensky says we have that's a well-posed boundary value problem. There exists a unique solution for any data. Okay, and what we'd like to do, though, let's say you'd solve that, you might want to know what the forces on each body are. That hasn't been written down yet. To do that, you need to define this thing called attraction, which it's basically a derivative, some kind of normal derivative of the velocity field. But what it's telling you really is how much force the shearing fluid applies to each point on the surface. Like imagine if I'm shearing fluid, then the traction is going to be a vector pointing along the surface. So with that, you can integrate the traction over the surface of one of the bodies, and that'll tell you the total force on that guy. And you can integrate the traction with a cross product, and then you get the torque on that guy. So this is how you extract the forces and the torques. So that's one problem. Given a bunch of velocities and angular velocities, please solve the boundary value problem and tell me the forces and torques. So that's the sort of prescribed motion. It's like we're dragging some objects through a fluid, and we want to know how hard is it to drag those objects. And you can think of this as imagine you stacked all of these as one big vector of forces. That's equal to some matrix, because everything is linear, times a big stack of the velocities. So, and just a little variant, if it could be that, you'll see this a little later, that we actually want to have a background flow, so that maybe these particles are actually not moving at all, but there's a big U0 fluid flow dragging fluid all by everything. And so what you would end up doing then is the U that you solve for here would actually be the correction to that background. So that's a technical detail. You don't need to worry about that much. Also, you could, if you had active swimmers, add a slip velocity on each body that would be like due to each particle, like pushing the fluid around. Like there's a little velocity here. Maybe they have little hairs that are pushing the fluid. So the boundary condition would be U equals V slip. Okay, so the other crucial problem is to basically flip this around and say, what often you really need is that there's a bunch of known forces and torques, and you want to figure out how they're going to move. So that's basically the inverse problem. It's called the mobility problem. So, and U is just the inverse of this big matrix. But you certainly wouldn't want to fill that matrix and invert it. It's going to be thousands, a size of thousands, but to even fill it would be ridiculous. So, okay. Any questions about that? That's sort of the math setup. So, okay, good. So challenges with this. You've got this elliptic boundary value problem that couples everything to everything. And if you're going to imagine updating the positions of all of these objects every time step, and they're all going to talk to each other, that's very expensive. So another issue, which I'll illustrate by showing you this movie, is, and this is some calculations that I did in 2D with, that Jun Wang did most of the work for, who is now back in China. And so have a look at this. This is a bunch of rigid objects, ellipses in 2D being sheared. And in fact, what you're seeing in colors is the pressure field. So you can see when they come close, you get pressure singularities or near singularities forming. Or if they're getting sucked apart from each other, there's a strong negative pressure. And they actually form these really fun force chains that, like, you can see there's blue lines going this way and red lines going this way sometimes as they sort of get crushed together. This is the effective viscosity. Remember, I was saying that you might want to care how hard it is to shear this complex fluid. And but you can see that the features are quite narrow where the particles, where those pressure singularities occur. So to go to 3D, back to 3D, what we care about, here's a solution of the force density, so the traction, remember that T vector, as two particles are, when they're very close to each other, the force vector is very large and concentrated spatially, and it's in a little area of, if the separation is delta, then the sort of the area in which the force is concentrated is square root of delta. So you'll get to see, and the peak is very large. The force peak is order delta to the -2. So that means you're going to get large, rapidly changing functions. How do you handle that accurately when you discretize things? Okay. So how do people solve these problems numerically? Well, finite elements is almost never used for this type of moving geometry because you'd have to remesh the exterior of all of those spheres every time step. And meshing is not that reliable or fast yet. Okay. You can discretize on you can set up an overlay grid. So you fix the grid and then have objects passing through the grid. But then what happens if two objects are closer than one grid point? There's no way to really resolve what's going on that grid. So this also isn't really a solution. It is used, so cut cells or immersed boundary methods. Okay, and then we move to things that actually solve the PDE already. This is precisely what Nilima said, particular solutions to the PDE. And, or they could be called Green's functions. So that you've already done something now. You don't need to discretize the PDE any longer. The chemical engineering community since the 80s has been using this thing called Stokesian dynamics, which means using sort of approximate tensors that tell you how two particles interact. Like if this one's moving this way, it'll tell you how the force gets transferred to another particle. Those are only long-range approximations. They have corrections. It gets a bit of a mess, but it's hard to say that they're not convergent. Like the correction just gets it roughly right. Apart from there's some work coming out of France that by Lefebvre Lepelot that's quite exciting, but she's only gone up to 4 spheres, but it seems to be convergent. So we're paying attention to that. And then there's this other idea that kind of comes out of Ricardo Cortez's work, which is taking the singular Green's functions, like a delta function, and smoothing it out to a Gaussian blob of force. So these are called sometimes rigid multi-blob methods or regularized Stokes slits. And they also introduce a length scale. So what happens when this length scale is too big to represent the true singular interactions here? Then you can't get it. You can't get the right answer in that case. Okay, so, and then boundary integral equations. So, which Nilima already motivated, right? These have a history in fluid problems. And we'll talk at the end about that. And what you can think of is that that's using force densities that live on the surface and generate fields, Stokes flows from those force densities. And they can be convergent and high order accurate. They're not always easy to code, but once you've done it, then they can be very good. And what I'm going to talk about, I mentioned method of fundamental solutions. Oh, all right. Let me just say one thing. What happens when these spheres, do they actually collide or not? That's a great mathematical question. Mathematically, well, does anyone want to have a guess? What happens to spheres if they're sitting in a Stokes flow and they're pushing up against each other? All right, JC's shaking his head. Right, as they get closer, the force gets stronger. Like there's a relation between force and velocity and the proportionality constant is sort of inverse with the distance. So basically they get actually exponentially close in time, but that's mathematically they never touch. But in reality, they are rough. So they will in touch in reality. So it's kind of, so which problem do you want to solve? That's even a question, a modeling question. Okay, but here's what people do in the community is they often say, actually, I'm not going to let the sphere get closer than 1.1 times its true radius because I don't want to have to design a numerical method that gets it right when they get close. So, okay, we'd like to get it right, at least. So we believe in convergent methods. So,
sorry, this does not introduce errors in the long-term flow?
Well, yeah, it does. It changes what the flow does. Yes. So, but you could argue that if this were like very short, if this was actually representative of surface roughness, then that would be a good model. But 1.1 is not, that's not a sphere. So, yeah. Okay, so I'm going to talk about method of fundamental solutions. And so this is like potential theory, but with the sources being off the surface. And they can be convergent, and they're really more used for acoustics and electromagnetics. So let me remind you, or maybe show you, what the fundamental solutions, so the Green's function for Stokes flow looks like in 3D. So this is like if you take a force at a point y is a point in R3, right? And then you look as a function of x, another like a target point, then you would get this flow field with the arrows here. And so again, x and y are not Cartesian coordinates. It's that x is one point here, right? And then which is kind of, and y is the source point, and you sort of think of a source and a target, right? And they're both points in R3. So what have we got? This already solves the PDE everywhere except at the point y, and it has incompressibility, and it has the correct decay at infinity. So we've hit 3 out of the 4 things that we want. The only remaining thing is the boundary condition. We haven't solved that. So what do you do? Firstly, you have to pick a representation. So you say that the velocity field is a whole bunch of these Stokeslets, they're called, with unknown strengths, lambda j. And those are vector strengths. So we're going to put, like a source strength, lambda 1, lambda 2, at a bunch of these interior points, and add them all up, and hope that we can now make something that solves the boundary condition. So I guess it's probably important this representation is going to come up again. So sorry, we may as well write it. Right, so yj are the source points, and lambdas are the source strengths, and that's what you don't know. So what you're going to do is take a bunch of surface nodes, which are these like open little dots here. The blue ones are the sources, and the open ones on the true physical surface. And you're going to, each one of those, you're going to say, that has to solve the boundary condition I wanted. UBC at one of the surface nodes. So each surface node gives 3 rows of a linear system, because there's 3 vector components. Okay, and you could abbreviate that big linear system now by G lambda equals U. And it's actually a rectangular linear system, right? Lambda is some vector here, and this is UBC is the boundary conditions everywhere. So that's the basic method. It sounds too easy, too good to be true. So you'll see, so it has a lot of good features, right? If you choose the separation correctly between the source points and the target, the collocation points, then you get smooth functions on the surface. That means you can use simple quadrature scheme on the surface, nothing fancy, just any smooth quadrature on your surface. You need a few more collocation points than source points. And the wonderful advantage compared to boundary integral is that you can evaluate arbitrarily close to the surface and even on the surface without doing anything fancy. There's no extra technology needed, no extra formulae. So, and that's not true for boundary integral. Okay, but what's the problem with this? Why is it, when it's not a universal solution, is that the condition number of these matrices are very large. And this little argument here, so just to remind you, condition number sigma max over sigma min, we could, as you try and shrink the proxy sphere, which has a radius RP, to be smaller than the true radius, which we're just going to call 1 through the rest of the talk, then you get more accuracy, but you also have a growing condition number, and those two have to happen together. So this may remind you of radial basis functions, certain things in numerical analysis. To get more accuracy, you have to pay with more ill conditioning. That's one of those situations. So why does that happen? Well, intuitively, the smallest singular value of this matrix, right? You've got a matrix that's sort of telling you how these points, how these proxy points are interacting with another concentric sphere. If you put think of a high degree spherical harmonic, and you might remember Laplace's equation in 3D. If you put a high spherical harmonic degree, then it decays like the degree, like the radius to the power of that degree. So that means that pretty soon the decay from RP out to 1 becomes exponentially, that becomes an exponentially small number. It's decayed very rapidly. That means there will be functions that you can place on these proxy points that have almost no effect on the surface points. And that's the source of ill conditioning. So here's a little graph that actually just shows as you shrink the proxy radius, RP, condition number is growing exponentially and hits inverse of machine precision. So, okay. So that means you can't just apply an iterative solver to this. You have to solve it in the least squares sense. So I've written this out now as our least squares problem with the L2 norm on the residual. You're trying to minimize the residual. Well, if we stick to small problems where we're willing to pay the n cubed cost, we can just do the SVD and completely stably solve these least squares problems. So what that means, just to recap, here's the SVD. And what you do is if you want to prevent sort of arbitrarily large blow up in the lambda coefficients, then you do a truncated SVD. So you pick a cutoff close to machine precision. You say, I'm going to invert the singular values, but only down to a certain level. And then after that, I'm just going to kill off those spaces and set them to 0. So, so what you get then is a pseudo inverse, right? So you've got the answer, the solution is flipping the SVD around, but with this regularization, hitting boundary data. And we can call this G pseudo inverse, right? So whenever you see the pseudo inverse, you actually have to, you're not allowed to fill this matrix G plus. You have to apply, you've got to keep two matrices like U transpose and V sigma plus, and you've got to apply one and then the other, because otherwise it's not backward stable. So that's a kind of fun fact that isn't widely known, certainly not in the rectangular case. But the fact that it is stable if you apply the two steps is quite nice. So if you only have a few thousand unknowns, this is a great technique. Okay, and you can solve it in a few seconds. So let's look at a little convergence result for that. Here we have b equals 2 with the number of spheres. So we've got two spheres next to each other like this. Proxy radius is like 60% of the true radius. What we're plotting now is the error as a function of putting more and more source points, proxy points on the inner sphere. And you can see beautiful exponential convergence in both the surface residual, so that's the maximum over the surface of how much it's matching the boundary data, and then the derived forces and torques. Remember, we can read off the integrals of those forces and torques. In fact, you can read off the forces and torques very simply. I think that formula will come up. So the other thing to note is that if we separate, well, by like 0.2, then that's the blue, you get a more rapid convergence. But then if you push the spheres closer together to be separated by 0.1, then the convergence rate has deteriorated. The slopes are now worse. So that said, if you want separations down to 0.1, this is a great technique, because with just, like only 1,700, so like about 5,000 unknowns, you get 10 digits in the things you want for that system. And the convergence, you can predict the convergence rate. I'll show you a little prediction for that. But you pay a price, and as they come closer and closer, you will fail if you just do this. Okay, so you might ask, well, a natural question is, how does this compare to boundary integral with the same number of unknowns? And the answer is, in our assessment against Chauvin Virapanini's work with Eduardo Corona, that it's the same, you get the same convergence rate. It's just as efficient per degree of freedom as boundary integral for spheres. But it's so much simpler to code. Okay, and you can do some more general smooth shapes. You can't do like a arbitrarily complicated aircraft or something. You'll end up with too many unknowns and you can't do the SVD. But for small, you could have a banana-shaped particle or something like this, and it would be fine. Okay, so we actually wanted to do lots of particles. So what happens here? The complexity is actually going to come from all of these particles, not from each one being, because each one is a simple shape, right? So imagine now you have the proxy sources on a body B prime. Remember we had this interaction matrix G here for one body. Well, now that has a G B prime, which is the interaction of those sources with the collocation points on another body. Okay, and each of those forms a block in a big block matrix system. It's a big rectangular matrix, and now you have all of the vectors of unknown sources on each of these blue dots, and you have the full boundary data. This is big ill-conditioned, just because each block is ill-conditioned, so the whole thing's ill-conditioned. You can't iterate on this, so you're kind of stuck, perhaps. So, but one way that you can actually iterate on this is to say, let's do a block diagonal preconditioner. It's kind of the first thing you might try, but we hadn't seen this done in the MFS method of fundamental solutions setting. So what you do is you say, well, I'm going to change my unknowns from these lambdas to mu's, where mu's, where the lambdas become mu's by hitting with the one body pseudo inverse. So what that's doing is it's saying, okay, you started out with the blue dots as the unknowns. Actually, you want the unknowns to be surface degrees of freedom on the physical boundary. So that's what the mu's are. And then this little block diagonal sort of formula is the solve that gets you back to the blue sources in each body. So, okay, so all I've done is inserted that formula into the above, and the G's now sort of pile on here so that each column gets a stack of pseudo inverses on it. Okay, and then, so what? The problem is that you remember that G was actually a tall matrix because M is greater than N. Well, so in that case, G hitting G plus certainly cannot be equal to the identity because it just doesn't have enough rank to do it. So instead, you just say, well, actually, it's trying to solve the problem of, it should be that if I give it any surface vector, it can reproduce that data. So you actually just replace each diagonal block by the identity, which it's a sort of numerical discretization of. And so now we have the same system with identity blocks down the diagonal, and then that works beautifully. So let's abbreviate that by this big G tilde. And this is huge and square and well conditioned. And now you just do geometries to iterate on it. So you've got rid of the ill conditioning. Okay, so let's just do a little example of this. You certainly don't want to fill the matrix. You want a fast way to apply G tilde. So how do we do the matvec? When you do a Krylov space, you need to do method. You need to do the matvec. So remember, you're trying to solve G tilde U, the stack of U's equals boundary data. Okay, so the first thing to do is apply, you've got the mu's, you want to go the mu's, the surface data back to the proxy point strengths for each body. You then have all of those proxy point strengths. You want to just apply the Stokes kernel to them and evaluate it at all of the surface points. So that's a big all-to-all evaluation of a PDE Green's function. So that's something that the fast multiball method is designed to do, for which there's various softwares, FMM, various things. Actually, these are all at Flatiron Institute in various ways. And so we'll treat that as a black box. You generally can go to it does about 10 to 100,000 points a second on a typical per core, I guess. So, on a old laptop or something, depending on how many digits you want. So that's the main step, is that the main cost is there. And then remember, you had diagonal blocks that should actually be I. So you subtract off what you just did wrong on the diagonal, and then you add in the block itself on the diagonal, and that just puts the I's on the diagonal. So that three-step procedure does a matvec by this big square matrix, G tilde. And then you can solve the thing with geometries that way. And then finally, you can use this representation, remember the representation here, to evaluate the field wherever you want and plot traces or whatever you want. So, and the nice thing is you can evaluate the net forces and torques just because each little proxy point provides force. So you just sum up the proxy point's forces. You don't even have to evaluate traction on the surface. Okay, so that's quite a nice procedure. Now for large-scale problems, let's see a couple of results for that. So we're going to give a bunch of spheres some random motions. It's like 2,000 spheres sitting in its kind of plane. They're not too close to each other. They're 0.25 separated. And that means that the system is still relatively well conditioned, and you don't need that many unknowns or surface points. And you can solve on a very old desktop, it turns out, in a few hours. It still takes a while, but you're getting, by the way, the solve, I didn't say this, but you're getting a solve to, yes, here we go, 3 digits for the surface data and 5 digits for the forces and torques. So, okay. You can also solve, remember that I said you could impose a background flow, and then you could solve for the field that cancels out the background flow on the boundary for the boundary condition. And then that sort of restores no slip boundary conditions to all of these red surfaces here. Amazingly, you can, in that situation, you can put the spheres really close to each other, like 10 to the minus 3, and you don't have to do anything fancy. You still just use a few hundred sources. And this is because there is no relative motion between the spheres, and it doesn't seem to induce a force singularity, right? Remember those red and blue peaks we were seeing was when they were moving relative to each other. If they're not moving, it seems like there isn't a singularity there. We see exponential convergence. That should be analyzed. I should have asked that as a question of the audience, but I forgot. So why you can get away with being so close even without refining towards that singularity. So it's an analysis question that I haven't seen the answer to. Okay, so mobility problems, well, so remember what we did was resistance problems. So now we want to flip it around. So one way to do things, so remember we were solving G lambda equals U boundary condition. Okay, the boundary condition you can write as some sort of column vector on the velocities. Actually, so this Km looks like that. No, it's the other way around. So Km looks like this. U is the vector of velocities and torques, velocities and angular velocities. And then this produces a big vector of boundary data, UBC. Okay. So this Km is a big tall matrix. So, and then you can extract the forces and torques once you've solved for the lambdas using a transpose matrix. So I won't draw that. So that's so if you want to do the mobility problem, you're actually saying that the boundary data is unknown, but we know it's of the form Km times something. And but we have a constraint now on lambda, so you end up with a constrained least squares problem. And that's sometimes done in the rigid multi-blob method as a saddle point problem. Okay, but we decided not to do it that way because we don't really know how to handle ill-conditioned saddle point problems. So what we did is we said, okay, here's an abbreviation for the representation. That's what we had here. U equals S lambda. Write down an orthogonal projector to the projector that takes you in the orthogonal directions of the column space of this big Km matrix. So that's saying, okay, and you're going to pick some solution lambda 0 that is already gets the forces and torques correct. So that's not too hard to find one. Basically, take the force, spray 1 over n of it onto every source point, and that will get you the force correct, the net force. Okay. So what you do is you set up a new representation that takes lambda, projects away, so takes the component that's, so I minus L takes the component orthogonal to these rigid body motions. You can think of these K and columns as surface velocities that correspond to rigid body motions. So, and then you've got a remaining part, lambda 0, which you've designed to actually supply the forces and torques. And the point is that this first term that you've added in has a lot of unknowns in it, but by design, because it has the I minus L, it doesn't contribute any net forces and torques. Because, and you can just check that by construction, this is the orthogonal projector to this guy, so that the answer is 0. Hope that's clear. It's a little, yeah. So, you know, this is the most algebra you'll see. Don't worry. So what that idea says, what you're saying is, okay, let's make a new representation, and now we want to. We still don't know this big U, the set of forces and a set of rigid body motions, but you make an ansatz that you have a little bit. You have a remaining space that is sort of unused, right? The space of lambda that you're using here is the stuff orthogonal to column space of Kn. So you can still use the column space of Kn to construct the unknown forces and unknown angular velocities and center velocities. So you this is something quite similar to a completed double layer formulation that's used in boundary integral. But we hadn't seen it used in fundamental solutions before. In particular, we hadn't seen any way to solve mobility problems using method of fundamental solutions. So what you've done now is, remember we were going to solve, originally it was G lambda equals some boundary data? Well, we decided that we were going to write a new representation which had this lambda 0. That's already known. So that sort of goes over to the right-hand side. And then we also had that the right-hand side, what we used to think of as the right-hand side, is unknown, but it's linearly dependent on u, and so we're going to insert u with minus knt times an unknown. So that's going to move over to the left-hand side. So this little pair here, actually, this matrix, sort of low-rank matrix, it is coming from that we didn't know the velocities in the first place. The net effect is that this thing still remains well conditioned. Well, let me rephrase that. If you take this new linear system, you can apply the one-body preconditioner to it just as before, and then you end up with a large well-conditioned block system. So, okay, well, that's the worst bit of algebra, but just how you get to see how you actually don't have to invert anything to like solve what looks like the inverse problem. Resistance and mobility can be related through these sort of low-rank updates and projectors. Okay, so let me show you some results for mobility. So this is actually the largest problems we've done on mobility. This is 10,000 ellipsoids. You can sort of see a zoom in here. They're not tremendously close to each other, but then this shows you the residual in log 10 of the residual. So you can get your 3 digits or better on every surface point. And they're not axes, they're not bodies of revolutions. You couldn't apply any tricks to do boundary integral would be quite hard. You have to come up with a discretization for these guys. And we have 5 digits in the actual motions that you want. What you're doing is you're pushing all of these ellipsoids with given forces and torques, and you want to see how they're all going to move around in the sticky fluid. So you get 5 digits in that. The thing involves around 30 million unknowns, and you don't need very many geometries iterations. That's actually an interesting difference, that resistance, as you make more and more bodies, the number of iterations grows, but for the mobility, it doesn't, and we don't really know the mathematical reason for that. So, okay. So let me show you what happens as you get close to each other. Lord Kelvin in 1853 showed that if you take the Dirichlet problem for 2 spheres with an overall electric field, constant field, you can actually iterate on an image reflection series. So you can say, C1, the sphere solution here is given by 1 charge, which reflects to this point, and then you can add, then that reflects back to this point, and so on. And those points accumulate at a distance which is the square root of the separation of the particles. Very interesting. It's geometric average of the radius and the separation distance. So, okay, could we do that for Stokes? And the answer is basically no, because it gets too complicated. Even if you reflect 1 point, it gives you a line density as the answer in Stokes. And then you would have to reflect the line density. But you do expect that the Stokes solution will look like something distributed on a line from the center out to this accumulation point. We don't know what. My approach to this is usually well, I think we do all right. So yeah, let's assume, and let's match as some analytic results, that you end up with some set of singularities between the origin and the accumulation point. So you now have to understand what MFS is going to do with this. You've got to understand, so MFS analysis considers that the PDE can actually be extended inside the sphere a little bit as a solution to the PDE. If the boundary data is analytic, so this is the theory of holomorphic theory of PDEs. If you have analytic data, you can continue it in a little bit, and actually that tells you, so you, and in this case, you know that you won't be able to continue it in any further than this accumulation distance, because there's a singularity there. So think of complex analysis. There's singularities nearby things in the complex plane. So, okay, so if you now try and say with MFS, what's going on? Well, you would like to, just to summarize this, if you have singularity in the continuation of the solution on the inside, on the non-physical side, then as long as your proxy points actually shield from that solution, then you get a stable MFS representation, meaning that the coefficients need not blow up. And you get a convergence rate that's controlled by this distance. So that actually explains the convergence plot that I showed you earlier. Why, as you bring objects closer, now we know that there's actually a singularity in the continuation of the solution, that singularity approaches the surface, and that's what ruins the convergence rate. Okay, so, but as I said, as you bring them closer, the convergence rate approaches 0, and you basically can't get any accuracy. So if you wanted to get to spheres closer than 5% of a radius separation, then it would become impossible with the standard method that I showed you. So what we did is we said, let's think about the multiple reflections. Well, we looked at this and we're like, this is horrible fractal that has a bunch of nice math behind it. We're not going to try and reproduce that. What if we just pretend that the pairwise solution involving two spheres does involve a singularity along a line, and let's just throw in some unknown sources along that line and let the computer do the linear algebra to figure out how strong those sources are. I'm a big, so there's actually a lot of literature sort of, especially coming from my boss Leslie back in the 90s with Hongwei Cheng on, at least in the 2D case with Laplace, figuring out how there's actually summing all of those sources up, using that as a new basis. In Stokes in 3D, that's never going to work. So my approach is actually just throw in singularities here, let the computer find the, use numerical linear algebra instead of algebra, because the algebra would be a nightmare. So, okay. And what we actually had to do was throw in different types of singularities. These are called rotlets and doublets. They have sort of various nasty formulae that I won't write down. And you also have to increase the node density around here. We did it in a sort of pretty ad hoc fashion. But that gets you now to much closer distances with only a few extra unknowns. So, okay, that was my philosophy. Be inspired by the elaborate analytic formulae, but make the computer solve for the coefficients instead. Okay, so what happens? Let's say we put four spheres very close to each other, kind of as close packed as you can, and this is the separation now. So 10 to the 0, this is like 1 radius separation, but here's what we really care about, down to about 3, 10 to the minus 3 of the radius. If you don't add in these images, then you lose all of your digits. If you do, you can maintain 4 to about 3 digits without much extra effort. So you notice we're using 20 images along these red lines, which is about, well, it's about 60 image sources along each red line. So it's not too bad. Okay, so with a few extra unknowns, we've been able to go 100 times closer. Now, GMRes doesn't really like this. So there's various things we've been trying to think about. You still have to suffer as the spheres get close when you use the iterative method. But at least for smaller problems, we can do that. We can put spheres a separation of 10 to the minus 3 relative to their radius and request 3 digits in the solver and get those 3 digits. So here's the residual. What Anna is doing now, I mean, Anna did all of the numerical experiments here and designed a lot of the schemes and the increase in density and optimize the parameters. But we have to insert the fast multipole and combine it with these image line enhancements to try and get a method that can do 1,000 spheres when they're very close. That's the next step. So I'm going to show you, we've got a few minutes left. I'm going to show you some of the slender body stuff. So we're going to switch completely to objects that look like this, and which appear in a lot of biological situations like actin filaments, pneumatic fluids, just fibers like paper pulp. And so there is a standard tool for this that says, replace this by a single line And then numerically, that's been, and write a line integral along that in 3D. And then numerically, you can discretize that line. And that's become the sort of the standard tool. One of the first things we did after we developed a solver that I'm going to show you a little sketch of is test how accurate is slender body theory. There are some theoretical results on slender body theory. It's really quite hard to prove actual math analysis bounds on, but Laurel Ohm has done a bunch of this. But as you bring two objects close to each other, the radius is epsilon for the objects. So when the radius is small, everything's good, blue is good. And the separation, but basically when the separation starts to become like 10 times the radius, then you start to lose accuracy. And when the separation is one radius, then you've lost all of your digits already. So slender body theory does not get you close to each other. So you're going to need something else. So we wanted a high order boundary integral method for this, and where you can dial in some number of digits you want. So using Nilimmer's nearly her notation, this is a single layer. Just going to call the double layer D. There's the formula for the double layer. It's some sort of nastier tensor object for Stokes, but there it is. And then you discretize the surface. So the type of discretization we use uses panels along the body center line, and then basically theta Fourier modes in each of those panels in the other direction. And then what we did is, I mean, Nilimmer explained this sort of philosophy, right? You set up the representation of the integral equation so that there is a half times the identity comes out. When you restrict that to the surface and use the jump relations, you get a second kind operator, so some multiple of the identity plus compact. And that means when you discretize it, you get a square linear system that's well conditioned. So I can't go into all of that, but I'll just flash a little bit of some of the technology that Daria developed. And that's to replace, you have to think of you have singular quadratures that have log singularities in one variable. You can replace that by things called generalized Chebyshev quadratures that use a lot less points, which means you can evaluate things faster. So, and a similar thing for integrals around circular loops. We're assuming a circular cross-section for now. And you want to evaluate at a target point X. You can build in advance a bunch of Chebyshev quadratures, so which is collections of these black dots that with weights that when you put in the integrand, even though X can get very close to the surface, it still gives you the right answer over it. So that's just a flavor of how you can get like 10 digits down to very close separations of objects. And Daria is sort of can do this math and also the C++ sort of HPC implementation with an FMM and so on. So I'm just going to really show you a movie of this because we're out of time. And what you're doing now is you're taking these rigid bodies, you're solving the mobility problem at every time step. That gives you right, the stack of velocities and angular velocities. And then that tells you how the bodies are going to move. That's an ODE, and then you time step the ODE. Everything moves. They're sedimenting under gravity, and then there's a bunch of technology for how to solve the ODE to high order. That's spectral deferred correction. This involves about 1.6 million unknowns, but it's done to 7-digit accuracy in time stepping, which is sort of unprecedented. So I'll show you what the sedimenting rings look like. The average density is higher in the middle, so everything pushes down. And then Daria, well, I can show you that again. And Daria has a code base with some examples that you can go and check out on this. So my job was mostly to code up the old slender body theory method and compare, show how that broke down, and anyway, and to prove some theorems. So let me conclude. So I've showed you sort of linear cost solvers for Stokes flows. It's hard to get the right answer when rigid objects come close. And so I showed you a method of fundamental solutions and also a little sketch of boundary integral technology for that. So here's some of the papers with Anna and Anna Karen, and then this one with Daria. So they're all within the last year. Here's Daria's code base. We want to obviously try and combine 3D, these close to touching spheres with a fast multipole. We haven't quite done that. But then there's all this collision handling. In reality, they will touch, and you have to decide what to do. And there's this whole things called linear complementarity conditions that sort of push bodies apart, but that has to interact with a time stepper. It becomes a bit of a nightmare, but so we may have to get into that, or maybe we can hand over our solver to other people who do the collisions. So, okay, and then I mentioned this Brownian case. That's a whole nother issue. So we'll see what happens with that. And many thanks to some other collaborators that helped with this work. So thanks so much.
Okay, so thanks a lot, Alex. So wonderful talk. We have time for questions. So
sure, you've been.
I volunteered. Nice.
Thank you. That was really lovely. So I'll go backwards. When you have these particles that collide,
Yeah.
so sometimes what the physicists talk about are hard collisions,
Right.
or soft collisions, right? And so have you thought about maybe tweaking what the collision strength is as things get very close?
Yeah, there's another way to handle collisions, as you say, right? And that's to actually to make some kind of potential function that says as the separation is 2 times the radius, this would be like the radius, right, of between the two centers, and then let's actually make a potential function blows up and that interparticle separate, right? So the problem is that that would be a soft collision avoidance. That then the time stepper gets upset because it's suddenly like very sensitive. You sort of have to take smaller and smaller time steps to handle this soft collision. Whereas with the hard one, it can sort of take a big time step, figure out that it's intersected, and then you have to solve. Then you have to iteratively solve some nasty linear complementarity thing to figure out where you should have stopped, and then figure out how much force to apply in that time step. Yeah, I don't know which is best here. And actually, Shiravan is a good person to sort of knows that the collisions better than I do. But yeah. All right.
Okay, other question? Felix?
Thanks. I pressed something. I hope it still works.
Yeah.
There was this projection
Yeah,
that you
get
did
right
with
to
the
that. Sorry,
pseudo
wait.
inverse, where
Yep.
you fix the diagonal blocks with identity.
Oh yeah, just
Yeah.
the basic resistance.
Yeah,
Yeah.
I was wondering. So do we know that before the fixing, the diagonal blocks are far enough from identity so that when
So
you
that-
subtract, there's no issues with
Back to that.
cancellation?
Well, okay. So what's going on? You really the subspace that it's not able to solve is high frequency junk.
Mhm.
Is entirely high frequency.
Yeah.
And that's not stuff you want to try and solve anyway. So that's one way to look at it. I mean, these things kind of come up in spectral methods too, right? And the stuff you want to project out is always orthogonal to all of the low frequency modes that you believe your solution lives in.
Okay.
So that's what's kind of going on with this. Like this thing that is not the identity is actually going to project onto functions of theta or theta phi that are oscillatory. So it's fine. And you could kind of, I mean, you can take this system, which is equivalent to this system, right? So you can actually check, did my solution change much by doing that? And it doesn't change much.
Okay.
If you've resolved things. Yeah, but that's a good question. So
Thanks.
This was really enjoyable, especially the 3/4 of it that I was here for. I was trying to get the coffee machine downstairs to work.
Sure.
Um,
It's terrible. I tried to, yes. Anyway.
yeah, garbage. The hot chocolate's a bit better. So I had a couple of questions. One was, so suppose that these spheres were fish. I saw your fish preprint yesterday, which is a lot enjoyable.
With Eva Canso?
Yeah.
Okay. Yes.
And so, like, this is a fun preprint from yesterday talking about self-reorganization and information transfer in massive schools of fish. And so,
The fish are just dipoles, actually, for us, by the
Right.
way. So they're very simple fish in 2D, and they each produce a dipolar inviscid flow field now. It's like the opposite limit. So, yeah.
so I guess, is there a sense of like, I don't know, local kind of transfer of like, you know,
Information between the
yeah,
spheres?
exactly. Yeah.
Well,
Well, they're not looking at each other, obviously, but like it's mediated through pressure, but
yeah, I mean, I don't, there are some interesting questions there. One thing that you might be getting at what you're asking is like, if you take a bunch of spheres and fix them and then push one sphere around, then actually the velocity, there's kind of shielding by all the other spheres. So you don't actually see that velocity field far away. But if you were to apply, like, to let them all be freely moving, so the mobility problem, and you push one, then they all move. So you kind of get a global long-range effect. So there's some shielding and long-range stuff, but I think that's the language to look at it in, is how does the interaction die with distance?
okay, thank you. And then the other question was, I guess, following on your answer to Felix, is there like a physical interpretation of the high frequency junk that shows up?
Well,
when you're-
no, because
okay.
it's numerical. It's
okay.
it's really, it's things that cannot be resolved, right? You're kind of thinking of spherical harmonics, right? So smooth functions on the sphere that involve just a few wiggles. You believe the solution lives in a space that, well, as you add more and more wiggles into the space, that the solution is closer and closer to that subspace, right? There's a, the numerical space, and then, the solution is sort of very close to it. So, and you're asking about that stuff, right? That vector, which is kind of just the little bit of high frequency junk, and that sort of goes away as you add more and more numerical unknowns, as it should if you're sort of doing a high order method. So yeah, it's just numerical junk, and you hope that it becomes smaller as n goes to infinity, right? That's the numerical analyst's paradigm. So
Got it. Thank you.
Maybe just a quick question. So in the representation on the blackboard, in the discrete sum with the kernel S, is there any difference from a numerical perspective, I guess, between this discrete summation compared to something like a continuous convolution, if you had tried to do so?
So
and from the least square perspective as well,
right.
Like if you do like a discrete least square or continuous one, from a numerical perspective, is there any trade-off or interesting?
Well,
thing
for the sphere, you could do this probably with not much extra effort using spherical harmonics that lived on an inside sphere, right? And then you would have your, spherical harmonic sort of force densities living here, and they would interact here. And in fact, so if you look at one of the papers that kind of inspired this, or made me think there's got to be a better way, was Shervan and Eduardo, so Corona and Vera Panini, who included doing this kind of simulations with those spheres. And I don't know, what did we do? The various flavors of solver. I can't remember where I showed them at some point, but they designed a custom thing that uses the fact that spherical harmonics, we know, and they have to be vector spherical harmonics. So there's a bunch of nasty formulae. So yes, if you're willing to handle nasty formulae that only applies to the sphere, then they're all equal. But my goal was like, well, I don't want to just do the sphere. I want to be able to do ellipses, maybe just do some more bendy objects, nothing too crazy, but just enough to like contribute to like where we have a large number of them. But you don't have any formulae. So you could put smooth densities, but then how do you evaluate them? Well, you're going to have to break everything down to a quadrature rule anyway, in that case. So if you're going to do quadrature, you may as well just discretize in the first place. And we don't notice that there wasn't even any quadrature weights. You just have unknown strengths. And as you know, the overarching philosophy says, let the computer solve for the strengths, and you do the minimum amount of algebra, right? So I think it would, you know, there's something in between. There's you could do line integrals, right? So a continuous source. You could do you'd have to do quadrature at some point. Yeah, I don't know. For general shapes, I don't see a way that you can avoid discretization and quadrature. But then I'm biased because a lot of what I do is discretization and quadrature.
Thank you.
Actually, that last question was very interesting. And I was thinking about what happens in that summation if you replaced the sum by an integral.
Yeah.
So what you have is a representation of your velocities as a single layer, but over a curve that's not the boundary.
Yeah, like
right?
a displaced single layer. Yeah.
Exactly, right.
Right.
And so if one had that as an interpretation,
Yeah, it's a first kind integral equation.
yeah, so I mean, of course, as you say, it's really nice because when you're evaluating on the boundary, you don't have to worry about anything singular because you're
Yeah.
off the actual boundary. But would that interpretation help you to explain why the I call it the regularization, where you just replace things on the diagonal by the identity? Would that help explain that? Is there a
I
continuous
think
analog?
the replacing on the diagonal stuff, that's sort of solver independent almost. Like that's just, it's almost like multi-grid. It's like a one level multi-grid. You can, if you're willing to solve local problems, you can, that are not too expensive, then you can build, that's basically building a preconditioner for a global problem. So I would say that's different. That's distinct from what you've just described, which is that you can have a continuous density sigma on a displaced surface interacting, and then you end up with a first kind integral equation. And then, so, you know, what's your training then? Do you do analysis before you discretize, like Kress would do?
Yeah.
And, you know, if you look at later in Kress's books,
Yeah.
there's first kind integral equations and regularization in God knows what dual systems or something. It's discussed, right? So you could regularize before you discretize, or you could discretize and then treat it as linear algebra, which is kind of my approach. So I don't know what there is to be gained. Certainly in the sphere case, you could probably put better analytic bounds on these condition numbers and things at the operator level.
Mm.
Depends what, you know, how much you like analysis. So,
A little bit.
so you might want to go
lot.
there.
A lot. All right. Here.
Okay, so do we have more questions? All right, so thanks a lot for a wonderful talk and of Alex. So let's thank Alex again.
Thank you.
So I would just like to remind you that tomorrow there's the second talk of Nilima, which is titled Math That Resonates. And on Friday, there's the second talk, which is also a grand public talk of Alex about the mathematics of sound and music, or music and sound. I forgot.
Yeah.
It's probably okay.
Both.
Permute them. Okay, so hope to see you all then.